Hello everyone, it's November 22nd. Well, pretty late today. Let's get to it. Delete a node in a BST. This seems to be I think I learned this in the algorithm class. But the exact mechanism, I kind of forgot. What I remember is it's difficult to remove something like on the right subtree. Like you have to go left all the way down, something like that. I might have done this before, actually. Oh, wow. Done it also last year. Yeah. Yeah, I remember. So it's a BST, right, and a key. Delete the node with a key. Return the root. Search for a node. If a node is not found, delete the key. If not found, then it's not. Number in the nodes, everything is unique, root is valid, and blah blah blah. I think, yeah, so if it's the left tree, right? If it's a left, oh man, hold on. If it's a left, then I remove it, right? Then I need to find, yes, I think the left tree is on the left side. If I remove it, I need to find its right subtree and the leftmost node in the left subtree of this one, because we need to swap with a node that is the smallest one that is larger than this, right? Because if we get something larger than 3, but need to be smaller than 4, and everything on the left side of 4 is larger than 3 and smaller than 4. And then we go look for the smallest, and then we swap this one up. All right? Now that is if there is something. But if the right tree does not have, so this one does not have anything, then we simply swap this one up. Which, yeah, we need to delete this one and swap this one up. Okay, so is that for every single one? How about we delete this one? We're gonna go right and we delete this one, just move this one up. Okay. If I have no right tree, so let's say 5, 3, 2, no 4, right? So I don't have a right subtree. Then I just remove myself. Yeah, that seems to be the case. 3 different scenarios, right? Scenario 1, I do not have a right subtree. Then I just delete myself. Everything is fine. Second, I have a right subtree, but the right subtree is just a leaf node. If that's just a leaf node, I just swap with the leaf. Well, I shouldn't say swap. I can do swap, right? I can swap. I delete this and I swap the value. Done. Yeah, we just swap. Wait, hold on. Well, we don't have to swap. I can just delete. Well, I'm going to delete this. That will be easy, and then swap the value. Yeah, let's delete and swap. But on the left side, we cannot swap because it could be many level down. And the third situation is we have something, we have a left. But what if I have a right and a right? Well, if I have a right and have keep going down, now in that case, I just need to move this up, right? I don't have to change anything. Let me think. Yeah, we don't have to change anything. Then swap is not good. We shall just delete this one, right? remove this and put this one in its place. Okay, so yeah, I think I remember. What should I put it? Then definitely not an easy problem. All right, it's not an easy problem for sure. Sure, it's not an easy problem, but we know how to solve it. It might take a while for me to write it though. It's not like straightforward. It's a complex algorithm. All right, so delete node. I have root, I have key, right? Do we need to do another one? Actually, we can search for the node first, and then determine how do we delete. I don't. Hold on. We can just delete node, right? And then we can go down, and we're gonna find it first. And once we find it, yeah, we just delete node means we find it first. But then I need the parent, right? I need the parent, the current. So I need two levels, the parent and current. So I need a helper which has a parent. That's gonna be a tree node. And node, that's going to be myself. Hold on, what if I don't find it? Then we don't do anything, right? It has not contained. So we need to look for it first. And if we don't find it, then this one might be optional. That's true. This one might be optional. And we don't have the pass key. This one will return an optional tree node, right? So, as helper, we're gonna first look for it. We're gonna go if not node, and return none. All right. If node.val is larger than key, so node.val larger than key, that must be on the left side. So we're gonna just return. Actually, node.left equal to helper. Parent is gonna be node and node.left, right? Elif node.val is smaller than key, and node.right equals helper, node, and node.right. Else now it's equal, so we found it, right? We found it. So blah blah blah, and at the end we're gonna return node, right? So this is where we're gonna do the magic. So we find it. So node.key, node.value equals key. Then we're gonna check, right? If node, if not node.right, right? So we say we do not have a right subtree. We only have left. Then we simply remove myself and then connect. So we just say, how do I remove myself? I say parent, because am I the left or am I the right to the parent? Alright, I think I need another one. We call it a left is left. Right, is left, that's going to be Boolean value. So we go left, so I am left, so that's a true. This one will be false, right? So if my node, I don't have a right tree, right? If I do not have a right tree, well, what if I'm on the right side? On the left side, just remove this up. What if I'm on the right side? I have something like on the left, and I don't have a right subtree. Oh yeah, it's the same thing. I just move my left up, right? If I do not have a right subtree, I just move whatever is on my left up. So if not node, hold on, I have a message. All right, I'll go back. If node not node are right, so we don't have a right node, then we say if is left, which means I am the left child of my parent. Then we say parent dot left equals node dot left. Done. Right? Parent dot left equals node dot left. So this one, then we done. Else parent dot right equals node dot left. Done. Aleph node dot right, right? Now we have node dot right. If we have node dot right, can we combine the two situations together? Right? So what we want is to look for the leftmost, and then this one, the leftmost is itself, right? Oh, that's different because we're gonna swap. That is a swapping, and I'm gonna remove the leftmost. So, So we say if node dot right dot left, right? If not node dot right dot left, which means this one does not have a left child, then we just put this one up, right? How do? We say if is left, then parent dot left equals parent dot left equals node dot right, right? Parent dot left equals node dot right. So this one move up, and node dot right dot left, right, equals, okay, and then node dot right dot left equals to node dot left. Node dot right dot left equals node dot left. Same here, node dot right dot left equals node dot left. So this one connect up, yeah, that should be fine. So that, and else we're gonna say parent dot right, say from the right child. So parent dot right will equal to, right, will equal to same thing, node dot right and node dot right dot left. So this is the same. I can just do it here. Okay, so that's the two scenarios. Else, so this corresponds to node dot right dot left. I have something, right? Then what do? Now I have a parent which don't want to change. Actually, in this case, parent doesn't really matter anymore. Right? We don't really need to worry about parent anymore. This is a node, so that can be the new parent, right? And I just need to go from here, just go all the way down, and then when we find it, yes, and just set a new parent. But I don't want to change subparent, called subparent. So subparent is this, right? So else we say subpar equals node dot right and subtree current equals node dot right dot left, right? And then we simply say while subcurrent. Oh, while subcurrent. Now we keep going left. Subcurrent will be nothing. No. So while subcurrent dot left, right? And then we say subparent equals subcurrent equals subcurrent dot left. So we keep going down the left until we hit the last one where subcurrent is the left leaf, right? So when we hit there, we're going to do a swap. How do we swap? We say node.val subcurrent.val equals node subcurrent.val node.val. Right? So we swap the value, and after swap, we need to remove subcurrent. How do we remove subcurrent? Subparent.left equals none. And then when it's all done, we return node. Right? So when we do this, we're going to call helper. Parent is root. Oh. Uh-oh. Well, I mean, with start can just be none. I don't need start with this is a root. Is a left. Holy guacamole. We need a wow. We need like a dummy node. Ew, that feels stupid. That feels stupid. How do we do a dummy node? Well, we don't need a dummy node. There's just none, because the parent is not used. And I can just, because I say, yeah, we do need a dummy node. I just realized we do need a dummy node. Okay, because the root, right? We can't have the root is the thing. What if we want to remove the root? So I have a dummy node. Let's just say put on the left side. So I have a dummy node, right? And node.val equals, and if not, let's just say we remove 5, right? If not node.right, well, we have node.right. If not node.right or left, so this is this situation. If it's left, this is the parent. If it's left, yes. Then parent.left equals node.right, so this one will move up. Yeah, I think that's fine. I think it's fine. So we do have to have a dummy node. So we have a dummy equals tree node. Val equals a gigantic value. So 10 to the 5th. I just go math.infinite. Right, so value can be math.inf, left equals root. All right, so left is root, right it can be none, and this can be dummy, and left is true, right? Left is true. So this one, what will this one return? This one will return the node. It's not returning the parent, it's one will return a node. So I should just return this. It's like a dangling pointer because dummy done. That doesn't matter. Doesn't matter. All right, let's try this. Oh. I have confidence. Let's run both. Actually, all 3 of them. Ew, ugly. The hell. Output. The first one is not right. I did not remove 3. What? How? Did I even find 3? Apparently I did not find 3. I output 3. Okay. What the hell happened? If node val is larger than key, I look for the left, right? The node val is too big, I look for the left. Okay. So parent is node, and node on left. Okay, so this node, if node val is equal to key, it's right here, it's equal to key. And then I say if not node or right, that's not true. If not node dot right dot left, so it's the second situation. If it's left, that's true. Then parent should be this one, right? Parent dot left equals node dot right. So parent dot left equals node dot right. And node dot right dot left equals node dot left. Yeah, I think node is getting removed. And I return node. Oh, it's not return node. Okay, I see what the problem is. Okay, so in this situation, if not, but still, it shouldn't output this. I feel weird. Anyway, so if not node on right, and parent dot left equals node dot left. Parent dot left equals node dot left, right? And that's it. Parent dot left equals node dot left. So these two connected. Okay, I don't have a right subtree. Then what do I return? That is a good question. What do I return? I mean, I'm already manipulating, right? I don't think I should return anything because I'm manipulating along the way. Therefore, I don't think I should return anything. I should return none, right? And then, if not node, I just return. If this, I just go helper. Right? I don't have to return anything. We go here, I don't have to return anything. And we don't have to return anything. I just do it. And we do need to have this. And I'm going to call this. And I'm going to return dummy dot left. How about this time? We don't return anything. There we go. When you don't return anything, everything's right. Submit. Oh, I got wrong answer. Alright, show me. I remove 33. Jeez, it's a huge tree. The heck? This is alright, 31. And move 35 up. I did not move 35 up. Where's my 35? Holy guacamole. Every time, right? I think every time I write this answer is going to be wrong. Shoot. Tree visualizer. Jeez. This is a huge tree. I think I need to get even larger. All right. My God. Can I? Oh, I can go up and down. All right. So this one, I believe, is 33. So where's 33? Here. Right? So I should just move 35 to 33. So 33, we can go here, here match. So I go right and left. That's good. So we go, oh, I see. See. I need to find the left. Ah, I see. I need to find the left on the left subtree, the left node. Basically, is the smallest, right? That's what we're trying to find. Wait, hold on. I cannot move 35 up. I can only move 34 up. Oh, 34. If we move 34 up, how do we handle this? So basically we have to, so that's the same problem. We need to delete this one. Jeez. I see. So basically the problem becomes, we want to delete 33, right? So I need to swap 34 with 33. And then we need to delete this node. How do we delete this node? It's the same thing, right? This is a tree itself, so I have to delete this node. How do we delete this node? We say this. I want to delete this. No, we look to the right, right? And the right one has a left, so we move this one up, and we delete this one. I see where this one is going. All right, so we have recursion. Sweet Jesus. That's fine. That's fine. Doesn't matter. What matters is we do have to return a node, right? So I have to change the code a little bit. We don't need parent. We can just return. Okay. The left equals this. Hold on. Let me think. If now eval the left is equal to helper, whatever, right equals to helper, whatever. Okay, that's good. And it's here. If this, then we simply do we need left or right? We don't need left or right. Left or right is indicated here, so I don't need this, right? Why do I need this? I don't need this. I do not need this. I just need the next node. And basically, I just say return, right? Just return node or left. If not node or right, I just, so like if I don't have a right node, I just return my left child, which my parent will connect with my left child, so I will be kicked out. That's fine. So if not this, then I need to do this first, right? So if now node, the left, the right, I don't have that. Then I just say node, the right, the left equals node, the left, and I'm going to return node, .write. So we're going to return node.write. Right? All right. I actually simplified it tremendously. Last case, right? Last case. Subparent. Ooh, do we need subparent on this? Yes, we do need subparent on this. So subparent, subcurrent, blah, blah, blah. Now we have this. Now we're going to swap, right? We're going to swap. We say node.val equals subcurrent.val. Okay, let me see this one again. Hold on. We swap these two. Yeah. So node.val, we're gonna swap. Hold on, what happened? There you go. So node.val and subcurrent.val, these two need to swap. All right. Now after they swap, then I need to run helper again. After they swap, all right, let me think. So this, I have the parent, I have the subparent and subcurrent, right? And subcurrent and node I switch value. Then I need to say, so node.val they sub. Then I need to say subparent.left, right? Subparent.left will equal to helper subparent.left. Remember, we swap the value, so the left value is actually the key. So we're going to remove this, and that's it, right? And what do we return on this one? Right, so if this, node.left, otherwise node.right, otherwise I handle blah 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 blah. I handle everything, and we're gonna return node. Is that right? Well, for one thing, I'm already returning here. Right? I'm returning here. I'm returning here. These are returned, and for this thing, that's the last situation, right? That's the last situation. If this is the last situation, subparent left equals, so this will be all done, right? Once it's all done, yeah, I think this is return node. Because I'm not changing the node. Node is not being cut out and put something in. I'm not changing it. I'm just swapping the value. And when everything's done, I do return this node. So dummy equals this. All right, let's try this one. Let's see how this one fares on this. Run code. Ugh. Oh, that's fine. I don't need dummy. Oh, if I do this, oh, it's fine. I just help her root. I think we got it. And I just realized one more thing. We don't need, right? We don't need, like I do this. I don't need a dummy. Why do I need a dummy? Right? I don't need a dummy. Not only do I not need a dummy, I don't even need a helper function, right? I simply just go right in, right? I can go right in and just return node. If not, actually, it's not going to be node. Okay, I'm going to have to code it here. But all the node will change that into root, right? And we have to pass the key, unfortunately. Oh, and have passed the key here as well. And this is not output self dot delete node. All right. Okay. Same old, same old. We're gonna try it again. There's no helper. Shoot. Self dot delete node. All right. Okay, that's correct. Let's use test case or the other test cases. There we go. This one shall be right. Come on. Come on. Come on. Yes. Why only have 39%? Oh, there are a lot of people who are working on this. That's fine. All right, so this is the one. So we did better than last time. Last time we struggled, and this time, well, we struggled a little bit. A little bit. Well, that's 450. So this is a classics. This is a classic. I have done it before and learned it from my algo class. But still, this problem is challenging because of all the edge cases. Not really edge cases, it's all the cases, right? All the cases that need to be considered. My first attempt, right? My first attempt failed to consider the situation, right? Situation where the most left node of the current node's right subtree can itself have a right subtree. This means we have to run the delete function recursively on the leftmost node of the current node's right subtree. This is all log n, right? This is all log n, and we run it at 77 milliseconds. And I think we don't have to really look into the discussion. We've done it before. I'm just going to check my previous answer, make sure everything is clean and tight. Shall be it. All right, so root is none, ba, 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 ba. Nice. If root dot right is none, I return root dot left. Yes. If root dot left is none. Oh, that's way different. Root dot left is none, return root dot right. And most, oh, that makes sense. That makes sense now. Because I don't have to check this. I just check root dot left. And then this case can be included in this case because this will jump out immediately. And we will swap the value. And subparent. This will be subparent dot right. The root dot right. Hold on. Let me think. The most left is root dot right. Minimum value. Okay. So while most left dot left, blah 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 blah, we get the minimum value, and root dot value equals minimum value. We swap it, and root dot left equals self dot delete root dot right root dot val. So we delete the minimum value. Ah, I see. How about you? Well, subparent, subroot, right? And then if this dot left, what if it's by itself, right? By itself, and we'll jump out. Then we'll swap these two, and subpart left. No, this won't work. This one works because I consider this one already. So it's slightly different. Slightly different. I like this way. I like this way. So basically we say no right tree, right? Or we have a right tree, but the right tree is just a node. Or the right tree has some left stuff. And then we can go on the left, left, left until we find the subparent, right? And the subparent and a node. And we're gonna swap the node, and we're gonna do a bit more delete. I like how this one is thinking. I think if I encounter this problem again, the thing to keep in mind is we have to do this part, right? We cannot just go for the left subtree and that's it, because the left subtree might contain like a right subtree, sub-subtree. So after we swap the value, then I need to run the delete again. Yeah. Okay. All right, that's it. Well, it's kind of late. I know. Oh, I forgot to upload this. I don't think I can do another medium. Let's roll an easy one. All right, let's roll an easy one. Not really roll an easy one. Just do an easy one. All right, which one we haven't done yet? Oh, we done. I was going to say everything. Path sum. How did I not do path sum? That seems to be something that I already done before. Come on, it's so slow. All right, path sum. Given the root of a binary tree, an integer, target sum, return true if the tree has a root to leaf path such that adding up all the values along the path equals target sum. A leaf is a node with no children. Okay, so you want to write definitely DFS. Yeah. 1, 1, 2. DFS, I think it should be very straightforward, DFS. What do you think? Root target sum, so I need that DFS. Node, optional, tree node, We don't have target sum, we just have the current path sum, right? Boolean value. We say if not node, hold on. Has to be, so if node, we say path sum plus equal to node.val. If node, if not, node.left and node.right, right, and path sum equals to target sum, then return true, right? Otherwise, are they all positive values? Nope. Otherwise, we say if node.left, let's not change the value. Wait, should we change the value? Yeah, we should. If node.left, if node.left, so this is just like not right. So if it's not right, and we have node.right, node.left, then we need to go. So we say if node.left and DFS node.left path sum, return true. If node.right and DFS node.right path sum, return true. Otherwise, return false. And this one can be simplified. Actually, not really that simplified. Or, right? Or return true. Otherwise, return false. Now, when I return DFS root 0, right? And now when I add it, and check. If not, yeah, this one should be right. All right, let's see. Wait, did I run it? Nope. Oh, what the heck? Ugh. True, false, false. I got all false. Ow. If node.left, yeah, I go this side. Node.left, left and node.right. The node.left is false, and or node.right, then we go right, and path sum added, and node.left. Oh shoot! And not. My bad. Forgot the not. There you go. Submit. Runtime error. Jeez. My lord. So, if not node, right, return false. If not node, return false. Which I like to do it here, right? I can return this if root else false. I can't believe I made a mistake. Right, if root else false. Okay. Do you want to do the other one? BFS? Well, think about how BFS will go, right? Talk about BFS will be a layer, another layer. Oh, write a summary. So this is BFS ON 57 18 BFS on a layer, and each layer we're gonna keep and have the node and the path, not the path, node and the sum, right? And well, we can do that. There's no reason why cannot do it. I'm gonna check the yeah, when I check. Oh, hold on. So we're gonna pass in current sum to this, right? So again, if not root, I return false. Q equals root and the root.val, and while Q temp equals this for node pass sum in Q if not node.left and not node.right, and path sum is equal to, okay, so where do we add? Actually, I don't like this idea. Right? Let's I'll pass this, right? And then we say path sum plus equal to node.val, and then we say path sum equals to target sum, return true, right? Otherwise, if node.left, then temp.append node.left path sum, if node.right, temp.append node.right path sum, right? And then we just keep going. Q equals temp, turn false. Okay, let's try this one. Yep, sounds right. It's faster. It is faster. This one is faster. But technically, it is also, right? So BFS, technically, this is also ON, but it is. Actually no. It's just for this case. It's also ON, but it's much faster. I'm gonna go at 35 and 94. Oof. All right, let's take a glimpse. Three lines. What? If this, return false. If value equals sum, and return true, L has path sum. Oh. Wow. This is very good. Oh, and I should just realize I just need to return this. Alright? Yes, I just need to return this. Oh, and you have this. Good. Very good. Yeah, I'm gonna steal this. we'll call it better DFS. Yeah, let's not look at it. All right, better DFS, we're gonna change target sum, right? So if not root, turn false. If root, if not root.left, and not root.right, and target sum equals root.val, and true. Otherwise, return self.hasPathSum root.left, target sum minus root.val, or self.hasPathSum root.right, target sum minus root.val. You courtesy it? No, I did not. This was back in 2015. Last edit 2000. Yeah, this one first posted 2015. Reference. It's a long time ago. Good question. It's a good question. Will evolve, right? These people probably don't do this anymore. This is, yeah. Officially, I think this is the right solution. Yep. Good. Good. All right. That's it. That's it for today. I got a bit lazy today, so I did an easy one. I'll see you guys tomorrow. Adios.